I am S. RAJKUMAR, working as an assistant professor for the Department of Electrical and Electronics Engineering in Marri Laxman Reddy Institute of Technology and Management. So today my topic is self-inductance. I am going to explain about self-inductance in magnetic circuits for the subject of network analysis and synthesis. So, what is the self-inductance? Here, the self-inductance is the property of a single coil. Property of a single coil, so which opposes any changes in the current in that same coil. So that property itself is called self-inductance of a single coil. So here we can see the property of a coil which opposes any changes in the current passing through it is called self-inductance. Simply the self-inductance we call it as a inductance of a particular coil. So that is the basic definition of a self-inductance. So here if we are increasing the current, so the current passing through the circuit or a coil or a single coil increases or changes or decreases. So whatever the magnetic flux linking with that coil is changes or increases. If current is increases through the coil, the magnetic flux linking with the coil is increases. If current passing through that circuit or a coil decreases, the magnetic flux linking with the same coil is decreases. So that is a case. So here the same coil changes and vice versa, then the EMF is induces in the coil or a circuit. So that EMF we call it as a self-induced EMF. Self-induced EMF of a coil or a circuit. So this is self-induced EMF in that coil. So here the induced EMF or voltage in that coil or self-induced EMF induces in that coil is given by L into di by dt. So that induced EMF directly proportional to, so EMF induces in that coil is directly proportional to rate of change of current through that coil. So by eliminating the proportionality, so we are getting di by dt. So this is a voltage or induced EMF. That induced EMF we call it as a self-induced EMF in that coil. So that self-induced EMF, here the self-induced EMF is because of the current passing through that coil. So produces magnetic flux. That flux, the flux produces in that due to that current is linking with the same coil. So the flux is produces linking the same coil. So that's why the EMF is induces in that coil or is given by L di by dt, where V is the self-induced EMF or voltage, induced voltage, di by dt is the rate of change of current. So the voltage induces in that coil is directly proportional to rate of change of current. So L is the constant of proportionality. We call it as a self-inductance of a coil. So this is definition for a self-inductance. Next, self-inductance. So when induced EMF is proportional to rate of change of current, it acts as a direction opposite to that described by Lenz's law. So I am explaining here by considering a coil like this. So this is a coil, a single coil or a circuit. So current is passing through this coil, magnetic flux is produces. So this magnetic flux, thus produced magnetic flux linking with the same coil. So this is the coil. So the flux produces in linking with this same coil. If current is changes, So EMF is induces. This EMF we call it as a self-induced EMF. So because of this self-induced EMF, the current is set up. So current is set up in the coil. So this current opposes. This current opposes the current. Current supplied to the coil. So here this is the current due to the self-induced EMF. So this is the effect of a coil. Here the cause is the current. So the applied current. So this is the current passing through the coil. Because of this current, self-induced EMF is produces. Because of this self-induced EMF, current is set up in that coil. This current is opposes the cause producing it. So the cause is supplied current. So that is nothing but a self-inductance. That opposition, the property of a coil which opposes the changes in current, changes in supplied current, that we call it as a self-inductance. That is the property of a single coil. So it is given by L is equals phi by current, where phi is the flux and I is the current passing through the conductor. So here the physical explanation. As I said that physical explanation is nothing but by considering the coil, if current is passing through this coil, magnetic flux is produces. So this magnetic flux linking with the coil, EMF is induces. That EMF we call it as a self-induced EMF. So because of the self-induced EMF, the current is set up. So induced current, this is the current set up by the self-induced EMF. This current is opposes the applied current according to the Lenz law. According to the Lenz law, this is the effect in a coil. This is the cause. Applied current is the cause. So whatever the current produces set up in a coil due to the self-induced EMF is the effect. So this effect opposes the cause. This is the Lenz law. According to the Lenz law, it opposes the cause producing it. So that is the physical explanation. That is nothing but when current in a coil changes, magnetic field associated with the coil is changes. So this change in magnetic field induces voltage in the coil, that we call it as a self-induced EMF, which assists the changes in current. So always it opposes the changes in current. That is opposition property of a coil, we call it as a self-inductance. So this phenomena is fundamental in inductors and crucial in AC circuits and energy storage applications. So this property, that's the phenomena, the opposing nature of a coil, that property we call it as a self-inductance, or simply we call it as a inductance of a coil. This is particular to the single coil only, single circuit, single coil. So here, so magnitude of self-induced EMF. So here we know that the flux in a coil, the flux in a coil is, I am writing phi by I into I. Here I is cancelled, the pi is equal to the line. The flux is expressed like this. I am expressing the flux is equals phi by I into current. So here, according to the Faraday's laws of electromagnetic induction, so induced EMF is given by minus n d phi by dt. So as long as the permeability is constant, here the permeability of a magnetic circuit is constant, the ratio of flux to the current, that means flux to the current, the ratio of flux to the current is constant. If permeability of a magnetic circuit is constant, the ratio of flux to the current is constant. So by keeping this constant, so if you are taking rate of change of flux, that rate of change of flux is equals to phi by I. This ratio is constant and permeability is constant. Permeability of a magnetic circuit is constant into rate of change of current. This current is changing. By changing the flux, the current is changing. So the rate of change of flux is equals phi by I into rate of change of current. So I am writing rate of change of flux d phi by dt is equals phi by I into di by dt. So that is equals d phi by dt is nothing but a voltage is equals minus n phi by I into di by dt. Here the term, so the term that is n phi by I. So this is the term. So this term we call it as n. This term is expressed is nothing but a quantitative measure of property due to which the coil opposes any changes in current. So this we call it as a coefficient of self-induced EMF, that is nothing but a denoted by letter L. L is given by self-inductance, or simply we call it as a inductance of a coil. So finally we are getting inductance is given by N into, N is nothing but a number of turns in a coil, phi by I. So this we can write it as phi by I, where phi is the flux linkages, flux linkages with a coil. So this is magnitude of a self inductance, or simply we call it as a inductance. So here the expressions for coefficient of self inductance, that is nothing but a self inductance L. So as we know that, so L is equals n phi by I. So we know that, so n phi, where phi is the magnetic flux, is given by mmf by reluctance. So mmf is nothing but a number of turns into current is nothing but a mmf. So S is the reluctance of a magnetic circuit. So L, if you are substituting here, in place of phi, if we are substituting here, L is equals n into ni by I into S. So this is the inductance. So finally we are getting L is equals n square by reluctance. So where we know that, so reluctance of a magnetic circuit is given by length by permeability and area of cross section. So a reluctance is directly proportional to length of a magnetic circuit or a coil. So mu is the permeability of a magnetic circuit, A is the area of cross section. So by substituting in place of S, reluctance, we are getting L is equals n square by L by mu into A. So finally we are getting, so n square. Finally we are getting n square mu naught mu or A by L. So that is nothing but a self-inductance is directly proportional to number of turns in a coil, square of the number of turns, and proportional to permeability of a magnetic circuit. Mu naught is the permeability of a free space, that is given by 4 pi into 10 power minus 7 Henry per meters. Mu r is the relative permeability of a magnetic circuits. So this is directly proportional to, and also it is directly proportional to A. A is nothing but a cross-sectional area, and inversely proportional to 1 by length of a magnetic coil or a magnetic circuit. So that is nothing but a L, self-inductance in terms of our coefficient of self-inductance is given by n square mu naught mu or A by L. So this is another way of expressing self-inductance or coefficient of self-inductance L. So next, factors affecting self-inductance. As we have know that, so we have seen that n square, L is given by n square mu naught mu or A by L. So these are the factors. So it is directly proportional to square of number of turns of a coil. This means for small length, if number of turns are more, the self-inductance of a coil is more. If number of turns are more, the self-inductance of a coil is more. This is a factor affecting the coefficient of a self-inductance. Second one, it is directly proportional to the cross-sectional area of a magnetic circuit. So if you are increasing cross-section area of a magnetic circuit, the self-inductance is also increases because it is directly proportional to area of cross-section of a magnetic circuit. Third factor is it is inversely proportional to length of a magnetic circuit. So if you are increasing the length, the self-inductance is decreases. The length of a magnetic circuit, it is inversely proportional to. So next, it is directly proportional to the relative permeability of a core. So for iron and other magnetic material, inductance is high, their relative permeabilities are high. So if you are taking iron or other magnetic material, so for any magnetic material, the permeability, the relative permeability of a magnetic material is high. So relative permeability is high, the inductance is high for iron and other magnetic materials. Next, third factor is air core and non-magnetic core magnetic circuits. So relative permeability is equals to 1. It is constant 1 for non-magnetic materials. So non-magnetic materials, the relative permeability is constant or mu r is equals to 1. So hence self-inductance of a coil is also small and always constant. So simply you remember that for magnetic circuits, for magnetic materials, the self-inductance or coefficient of self-inductance is high because the relative permeability of a magnetic materials are high. Self-inductance is high. For non-magnetic materials, so magnetic core circuits, non-magnetic materials. So the relative permeability mu r is constant. For example, here mu r is constant. The self-inductance is constant or small. So these are the two factors mainly affecting the relative permeability affecting the self-inductance of a coil. So next one is this one. So against this magnetic materials, current is or magnetic field strength is changed. So mu r is also changed. So if you are changing the magnetic field strength, that is H, magnetic field changes, mu r is also changes. Due to change in current causes change in value of self-inductance. So for magnetic material, it is not constant, but it varies with the current. This is a factor that since the relative permeability in iron varies with respect to the magnetic flux density, the coefficient of inductance is also varies. Similarly, if the conductor is bent on itself, magnetic field produced by the current through it will also opposite to each other. Hence, they neutralizes each other. Inductance will be 0. So nothing is there. If your coil conductor is bent back on itself, if you are bending, the magnetic field is opposite to the first half of a coil. So that magnetic flux is neutralizes. There is no magnetic flux, there is no induced EMF in that particular coil. So inductance is 0. Inductance or self-induced EMF is 0 in that coil if conductor is bent. If conductor is bent by back itself, so the magnetic field is neutralizes. When magnetic field is neutralizes, the inductance of a coil is 0. Next we are see what are the applications of a self-inductance or coefficient of self-inductance. So self-inductance is used in various electrical components. So we are using self-inductance phenomena in inductors, transformers, choke coils, tuning circuit, sensors, induction motors, inductors used in a relays. All this is self-inductance is used all the inductive coils. So choke is a inductive coil. So there we are using in transformer is also self-induced EMF is there, self-inductance is there. In transformers we are using self-inductance, and essentially for understanding transient behavior in a circuit. So self-inductance is used for or applicable in transient behavior, to know the transient behavior in a magnetic circuits. Next one, energy storage and store energy in a device. For the inductor properties, it stores the energy in the form of electromagnetic field. The energy storage, it is also applicable in energy storage or used for energy storage in a device. So these are self-inductance is concept is used. That phenomena is used in filter circuit for filtering applications. So all about the self-inductance of a magnetic circuit. These are the applications. So thank you. These are the references we are considering from the internet. And thank you all. Thank you.